Things are going all right. So on whatever day it is, Friday, we will have a quiz over solving equations, the stuff that we've been doing in this last section here. So let's finish off these last couple of problems that we didn't get to last time. And then we'll get into some new stuff. So we've talked about solving basic equations. That was in section 7.4 that we already had a quiz over. In this section, we were just talking about first starting with some identities to try to rewrite the equations into basic ones, or perhaps having a multiple of an angle on the inside of the function, and then having to work with that and solve for our solutions. The last problem actually combines a couple of those ideas, so we'll get to that. Let's use our half angle formula, though, to solve this particular one. So this particular example says we've got tangent of theta over 2 minus sine of theta equals 0. So again, our fundamental principle of solving these equations is, first, we don't like having arguments that are different. Right? That makes things harder. And then two, if we can, we'd like to write everything in terms of the same trig function. So first, typically, we will try to handle, pardon me, typically we'll try to handle the argument problem first, and then see if we can rewrite in terms of the same trig function, or perhaps do some factoring thing, something along those lines. Let's look at this one. Notice I've got a different argument inside my tangent than was inside the sine. So I probably should try to use one of our formulas for tangent, the half angle formula for tangent in particular, to see if we can rewrite this. What is one of the forms for the half angle formula for tangent? I need to look it up in your notes somewhere. There's a couple of different forms for that one.
One minus cosine 2x over sine 2x.
Yeah, so it was just an x, and it would be so the inside of the thing on the right hand side is double what's on the inside on the left, right? So instead of theta over 2 on the inside, here I would use 1 minus cosine theta over sine theta. The other one is sine theta over 1 plus cosine theta. This one's probably a little bit easier, so it'll make the clearing out the fractions a little bit better. So plugging that in over here, we've got 1 minus cosine theta, and then minus a sine theta equals 0. What do you think we want to do now to both sides of the equation to help us solve? We could do that. I'm not sure that's going to help right away, but you're right, we could do that. What's looking nasty to start with right now? Or what would we prefer not have to deal with? Let's put it that way. The fraction, right? So probably the first thing I would want to do is clear the fraction. So what can I do to clear the fraction? Yeah, multiply both sides by sine. When we do that, we'll get 1 minus cosine theta minus sine squared theta equals 0. Because I'll have to distribute the sine on both sides to both terms, right? When I multiply on the left-hand side. Now, the only thing we'll have to make sure that when we're done is that we don't come up with a solution that makes the denominator 0 in the original equation. Okay, we'll have to check. Remember, we talked about that last time. If you multiply both sides to clear the fraction, and we have something in the denominator that was a variable, we'll have to check to see if we got any extraneous solutions. We might get a solution that would make the original equation undefined, so we'll have to check at the end. All right. So we took care of the argument problem. That was problem number 1, right? We had mismatched arguments. So we took care of the argument problem. Now we've got mismatched functions, right? I've got a cosine and I've got a sine. So now we want to try to see if we could use an identity to help us write everything in terms of the same trig function. Can we? What can we do?
1 minus cosine squared.
Good. And we can convert the sine squared to 1 minus cosine squared. And then when we simplify this, we should get when we distribute the minus sign through, the ones will end up canceling. Get minus a minus makes a plus, so we get cosine squared theta minus cosine theta equals 0. And now this particular problem is not too hard to solve. What can we factor out of both terms now? Cosine? Oh my heavens. So we get cosine of theta times cosine theta minus 1 equals 0. So the first one says cosine theta is equal to 0. The second one says that cosine theta equals 1. When is cosine equal to 0? Yep, pi over 2, where else? So it was either pi over 2 or at the top or round down to the bottom, maybe 3 pi over 2, right? And it just keeps repeating. So it's pi over 2 plus multiples of pi. When is cosine equal to 1? That would be negative 1. 0, 2 pi, 4 pi, right? So multiples of pi. So from the last equation that we came up with, we'll get odd multiples of pi over 2 or multiples of 2 pi. Now, what we need to do, though, is make sure that these answers make sense back in the original, right? Because remember, we multiplied both sides by sine, correct? So you need to make sure we didn't introduce anything that was extraneous. Well, if I put in odd multiples of pi over 2, which is what this is, right? Pi over 2, 3 pi over 2, 5 pi over 2, so on. What's sine equal to at the odd multiples of pi over 2? Think about the graph. It goes up, down. That pi over 2 is up at 1, and 3 pi over 2 is down at negative 1. It just alternates between negative 1 and 1. So that's not a problem. So these are okay. How about the 2 pi, though? If I put in multiples of 2 pi for sine, what do you get every time? Sine of 0 or sine of 2 pi or sine of 4 pi, all those are equal to 0, right? So am I allowed to put in multiples of 2 pi into that original equation? No, because it would make the denominator 0, right? So these came out to be extraneous. So we wouldn't include those solutions. We would get those solutions instead. So again, we have to be careful. Anytime that you multiply both sides of an equation by something with a variable in it, you might make a false statement true. So you always have to check those solutions when you're done. In this case, we can't use the multiples of 2 pi because it would make, well, in particular, make this expression undefined, but we see it really here, right? We get 0 in the denominator. Questions on that one? That's okay? All right. Let's look at the next one. Same concept. We start off with two trig functions that have mismatched arguments, right? The argument on the left-hand side for cosine is just an x. The argument on the right-hand side is x over 2, right? So we have mismatched arguments. So I need to handle that first. Let's make the arguments the same if we can. So we want to use that half angle formula for cosine. You remember what that one is?
Plus or minus root 1 plus cosine x over 2, 2x over 2.
Yeah, so again, the argument on the inside of the cosine is on the right-hand side is double what's on the left. So plugging that in, and remember again, it's not quite always plus or minus, right? We have to remember it depends on what quadrant the x over 2 is in to start with. So yeah, that may play in at the end for our solutions. Now I've got an equation that has a radical in it. What do you think you might want to do to make that radical go away? Square both sides. And then we're going to have a similar issue that we just had. Okay? When you square both sides of an equation, you can also make a false statement true. Right? Maybe one side's equal to 1 and one side's equal to negative 1, which is false. But when you square both sides, you get both of them are equal to 1. That's true. Right? So again, at the end, we're going to need to check the answers that we get and see if they make sense. So when you square both sides, it makes the radical go away. It also takes care of your plus or minus. We should probably go ahead and multiply out the left-hand side. Oops, that'll probably help us out a little bit. I did not do myself any favors with this particular problem so far. So when you multiply out the left-hand side, you'll get a 1 plus 2 cosine x plus cosine squared x. Make my life a little bit easier and multiply both sides by 2 to get rid of a fraction. So multiplying both sides by the 2, you get the 2 plus 4 cosine x plus 2 cosine squared x. algebra fun so far. Now what do we want to do? Set it equal to 0, right? When you move everything to one side, good, because we got that quadratic equation, right? So moving everything over to the left-hand side, we'll get 2 cosine squared x plus 3 cosine x plus 1 equals 0. Does that factor? Well, yeah, you need a 2 cosine x here and a cosine x there. And then what are the constants going to be? I got a plus 1, right? So they better both be plus 1. Right? Because that'll give me a 2. When I multiply these two, I'll get a 2 cosine x, and then I get a 1 cosine x there. So when I add them, I'll get a plus 3. So again, setting each piece equal to 0, the first one tells me that cosine x is equal to what? Be negative 1 over 2, right? Because I have to subtract the 1 over, yep. And the other one tells me cosine of x is equal to negative 1. So far, so good. When is cosine equal to negative 1/2? Well, what quadrants are we looking in? Second and third. Cosine equals 1/2. Where? What would be your reference angle for cosine being 1/2? Yeah, it'd be pi over 3, right? So what pi over 3 angles are in quadrant 2 and in quadrant 3?
2 pi over 3.
Good.
3 pi over 4 pi over 3.
Good. And then when is cosine equal to negative 1? Pi, good. And then multiples of pi past that. Now we get to check our answers. This is a little bit more challenging on this one. Remember, the reason why we have to check our answers is because we squared both sides of an equation, so we can get extraneous solutions when that happens. Okay? That one gets a little bit more challenging. Let's do the easier one first. And I'm going to go back up to the original equation, by the way. I'm going to go all the way back up here when I do this. Okay. Putting pi plus 2n pi up here says that I would divide everything by 2, right? Agreed? Okay. So really I'm putting in pi over 2 plus multiples of pi into cosine. If I divide everything by 2, right? Pi over 2 plus multiples of pi. Well, we already said in the previous problem, when I do pi over 2 plus multiples of pi, what does that make the cosine equal to? 0, right? So the right-hand side, for pi plus 2n pi, the right-hand side will always be equal to 0, right? If I put in pi plus 2n pi into the left-hand side, I still get 0, right? So this, because that was how we found this one, isn't it? Cosine of x is equal to -1. So if I put in pi plus 2n pi in here, I also get 0. So pi plus 2n pi works, okay? That's okay. That one's okay. But let's look at the next ones and see what happens. All right. Let's look at this one. If I divide, the thing about the right-hand side, if I divide by 2, you get pi over 3 plus multiples of pi. If I divide everything by 2, don't I? Correct? Okay. If I put pi over 3 in, I'm good, because these will both be positive. But what happens if you put something in like 4 pi over 3? If I use n equal to 1 and put in 4 pi over 3, what happens? Cosine of 4 pi over 3 is negative, correct? This is in quadrant 3. It's negative a half in particular. Can the left-hand side ever be negative? What's the smallest that cosine of x can ever get? What's the lowest cosine of x can ever get? What's cosine always in between? -1 and 1, right? So the smallest it can ever get is -1. So is the left-hand side ever negative? Not a trick question. If the smallest this can get is -1, can the left-hand side ever be negative? If I take something where the lowest it can ever get is -1 and I add 1 to it, what's the lowest it can ever get? 0. So is the left-hand side ever negative? No. So over here, half of the solutions are going to be extraneous. Okay? It worked for when n is equal to 0. It didn't work when n is equal to 1. It'll work when n is equal to 2 and so on. So really we get x equals 2 pi over 3 plus 4n pi. We have to actually go around another time to get that solution. I know it's weird. Okay? The reason is because, again, we squared both sides. Remember, this plus or minus here isn't truly plus or minus. It depends on the quadrant, right? Remember after the half angle formula, it depends on the quadrant? If we were in the wrong quadrant, we would get negative, and that can't be. We don't get that answer. The same thing will happen for the other one. We have to be a little bit careful. Again, if you divide everything here by 2, you would get 2 pi over 3 plus multiples of pi. 2 pi over 3 doesn't work, but 5 pi over 3 does. So you end up with 5 pi over 3 plus multiples of 4 pi in this case. You have to be careful. And then the final one is here. You're not going to get one that tricky on an exam, by the way. That was really messy. Okay. So you have to be a little bit careful. The whole point of this is not that it was confusing. The whole point of this is that you have to be careful when you do things like multiply both sides of an equation with a variable in it, like the first one, right? We had to check our answers. Same thing is true when we square both sides. We have to check our answers. If nothing else about the problem, were you okay to hear? That part okay? To get to hear? That's kind of the important part. I know this part was weird. I agree, this part's weird. Basically, again, because of this plus or minus issue, I have to throw out anything that actually makes it minus versus plus. Because this side can't be negative. And it turns out that essentially every other one makes it negative, so we have to throw them out. Which is why we've got this extra 4n pi piece rather than 2n pi. All I really care about this particular problem is that you understand how to throw it out, that we had to throw it out. not necessarily how to throw it out. Let's look at this last one, and then we'll get into some new stuff. This last one's not nearly as bad. It looks bad to start with, but it's not nearly as bad as it was. So we've got cosine of 3 theta minus cosine of 6 theta is equal to 0. When you've got mismatched arguments, I've said multiple times, we want to handle the mismatched arguments first, right? What if it were, instead of 3 theta and 6 theta, what if you had this equation to start with? What would you do?
Probably move everything to the right side and factor and put cosine to it, make it positive.
Well, if I'm going to factor, I want to make sure I have 0 on one side, right? Remember, if I have mismatched arguments, I want to handle the mismatch first, right? I can't factor anything out of this yet because that 2x is on the inside of the function, right? There's nothing I can really factor here yet. I need to do something with this thing first. Say it again. Not quite the even odd, but we do want to use an identity. Even odd has to do with having a negative on the inside and what we can do with the negative on the inside.
Do we have to change that to cosine 2x?
To what?
1 minus sine. No, that's wrong. We have to use a double angle.
You're right. We need to do one of the double angle ones. Yeah, I agree with you. We need to do one of the double angle ones. There we go. Yep, I want to do it 2 cosine squared x minus 1. And I want to use that particular one because that keeps the cosines the same, right? Agreed? Okay. So yeah, we want to use the double angle. Cool. All right, let's go back to this original problem. Why did I say let's first look at sine x first look at cosine x and cosine 2x. What do you notice about the arguments in those two functions that I have written up there? The original problem. What do I notice? Yeah, this one's double that one, right? Right? The 6 theta is double the 3 theta. So how can you rewrite the cosine 6 theta so that my arguments match? Notice here, this argument is double that argument. This argument is double that argument.
Would be 6 cosine squared x minus 1.
Not quite. You're thinking about the right idea, the right formula to use. What do you notice here? I agree with the cosine 3 theta minus 1. What's the coefficient out in front? It's a 2. Yeah, it doesn't change, right? All we're changing is the argument. Basically, I'm just doing a substitution. This is like the x. This is the 2x, right? Just doing a substitution there. All right, so now we want to factor. In this case, I will get my signs rearranged. If you distribute the minus sign through, you'll get a minus 2 cosine squared 3 theta and a plus 1 I just multiplied everything by -1, so it makes that leading coefficient positive. This one should factor for us. Oops. We're just using the cosine 3 theta as the variable. I need 2 cosine squared of 3 theta, so one of them needs to be 2 cosine 3 theta, and the other one's cosine of 3 theta. I need a +1 and a -1, so I play with the signs. And I use the -1 with the cosine and the +1 with the 2 cosine. That should make everything work out nicely. This looks like a lot like the previous problem we just did, doesn't it? Set each piece equal to 0. We get cosine of 3 theta is -1/2, or cosine of 3 theta equals 1. We just said in the previous problem that cosine is equal to -1/2 at 2 pi over 3 plus multiples of 2 pi, 4 pi over 3 plus multiples of 2 pi, and it's equal to 1 at multiples of 2 pi. I guess it's -1, so this will be multiples of 2 pi in this case. Remember, when we're solving problems, when we have multiples of the argument, we just treat it like an x to start with, and then what do we do next now to solve for theta? Divide everything by 3. So we'll divide by 3 all the way through, and we'll get theta is equal to 2 pi over 9 plus multiples of 2 pi over 3, or 4 pi over 9 plus multiples of 2 pi over 3, or just multiples of 2 pi over 3. Notice literally the only difference in this particular problem was the fact that we've got an argument that's not just an x or just a theta. We have a 3 theta, but we solved the problem to start with just like we would treat it like it's an x, right? All the way to here, we're just thinking of the 3 theta as an x, aren't we? Right? All the way to here. And then the last step is just to divide by the 3. We've seen problems like that at the beginning of this one, right? So nothing particularly tricky about that one. Now, if you were asked to find all the solutions between 0 and 2 pi, well, in this case, we would have had 1, 2, 3 to start with, all right? And since we have a 3 in there, we would end up with 9. So you'd end up with writing down 9 solutions. You'd plug in 0 for n, 1 for n, and 2 for n to find the rest of them. Questions on that one at all? So again, your quiz on Friday will be over solving equations like these, not the nasty one, but equations like these where you've got to use an identity to help you rewrite. So make sure that you remember your Pythagorean identities and your double angle identities in particular. Okay. Those will be the big ones. All right, so I'm going to switch gears slightly for the rest of the semester and talk about a new coordinate system that's referred to as polar coordinates. So when you are doing regular old, what we refer to as rectangular coordinates, or Cartesian coordinates, both those things mean the same thing, or perhaps Euclidean coordinates, maybe somebody says that. when you talk about graphing, you talk about how far left or right you go and how far up or down you go to get to a point, right? But that's not the only way to describe how to get to a point, okay? So in polar coordinates is a little bit different. So let's say I want to describe, let's say right here, this point right here, the vertex of that angle is the origin, okay? Now in polar coordinates, we refer to that origin as the pole, okay? But we're going to talk about later about converting from rectangular to polar and back. You can think of that as just the origin, okay? From the pole, we talk about an axis that goes out to the right, which basically corresponds to your positive x-axis. We refer to that as the polar axis. And this will correspond to your positive x-axis. So the way I have this angle here situated, it's like we put the angle in standard position, right? Remember when we put an angle in standard way back at the beginning of the semester, when we put an angle in standard position, we put the vertex of the origin in the initial side on the positive x-axis. That's standard position for an angle. It's essentially what we've done here. All right. Our goal is to describe where this point is right here. Now, again, if you're doing rectangular coordinates, you would go, well, the way I have it situated, it'd go right and up, right? Your x would count how far to the right you go. Your y would count how far up you go. And if it's negative, it's left or down, depending on which is negative, correct? All right. But that's, again, not the only way I can describe where that point is. One way I could describe it is, how far is it from the pole? I could do that distance, right? So this would be your distance from your pole, or distance from the origin. And we refer to that as r. There's a reason why we call it r. If I take all the points that are a fixed distance from the pole, what kind of a shape do I get? If I fix the distance from the pole and look at all the points that are that fixed distance from the pole, what kind of shape do you get? A circle. That's why we call it r. It stands for radius. Okay. All right. Now, of course, saying how far it is from the pole isn't enough information to describe where the point is, right? There's lots of points that are the same distance from the pole. So another way to describe this, to figure out that I want specifically this point, we're going to look at this angle, the theta. Once I describe how far you are away from the pole and the angle that that segment makes with the polar axis, then I can get, I know exactly where this point is. So the polar coordinates for that point will be, we write the r first and then the theta. Okay, so the r is distance from the pole, distance from the origin. The theta is angle that terminal side would make with the polar axis, which is stuff that we've already done. So let's see how we plot points in polar coordinates. So notice what I've got at the bottom of the page there for you is a polar grid. Notice that the x and y axes there are superimposed. But here's a polar grid. So each of these concentric circles are the same distance from the pole, the origin, if you will. So all these ones that are right here are two units from the pole. So the one that's right here would be one unit from the pole. Okay. So we're slicing these up into circles. All of these other rays that are shooting out are angles, and you can see them all labeled on here, right? See the 5 pi over 3, 11 pi over 6, and so on around. Okay. So those are all the points that would make an angle of pi over 6 with the polar axis. This one would be pi over 3 with the polar axis and all that good stuff. Okay. So let's see how we would plot these things. The first one says I want to be 3 units from the origin, from the pole, and make an angle of 11 pi over 6. The way I typically do it is I count my radius first and then do my rotation. Okay? So a radius, a distance of 3 to start with would be right here. Right? Here's the distance of 3. That's not the point, but that would be the distance of 3 is on that circle. From this point, I need to rotate around clockwise because counterclockwise because it's a positive angle. So I'm going to go out 3 and I'm going to rotate all the way around to 11 pi over 6 and end up right here. So this would be the point 3. I'm going to label it as A so I don't have as many things on there. So you went out 3 units and then around 11 pi over 6 for your angle. Does that make sense? I'm going to erase this arrow that I put on here because this is going to make things messy. Okay. The next point has a radius of 2. So we're going to go out 2 to the right. But now since it's negative 2 pi over 3, which way should I rotate? Up or down? Down. Rotate around down 2 pi over 3 lands right here. Right? We end up here. 2 pi over 3 would be that way, right? So this point will be right here. This is the point B. Are we okay with point A and point B? Is this okay so far? It's okay if it's not okay. Is this okay so far what we got? Okay. Let's look at the next ones, because notice that my R has changed. I just said that your R is distance from the pole, right? Now I put a negative R value. That doesn't seem to make sense. This is negative, correct? It feels weird, right? I told you R is distance from the pole, and then I put a negative distance, which seems bizarre. I think it seems bizarre. Okay. But what does it really mean? Well, remember how we started to get these 2 points as I go to the right and then rotate? What do you think I'm going to do if I have a negative R value instead of going up to the right? Go to the left, yeah. So we'll go, then for that first point, we'll go left 1, 2, 3 units and use this as my starting point for the rotation. I'm going to rotate from here positive 11 pi over 6. So in particular, if I'm going to start my rotation in a positive way, from this point, am I going to go up or down? Which way is positive? Is it this way or is it this way?
Down.
Yeah, it's this way is positive, right? So from here, I've got to go downward because I need my same orientation, right? Positive angle direction is this way. It's counterclockwise. So I'm going to go from here and go down and rotate around until I get to 11 pi over 6, which is going to end up all the way over here. So we're going to start here. We're going to rotate around this way until I get all the way to 11 pi over 6, which is right here. So this will be my point C. Do you notice something about the relationship between A and C, by the way? Look at the coordinates and look at the graph. What's the only difference in the coordinates? You know, one's negative. Well, the R value is negative in one and positive in the other. What do you notice about the relation between these 2 points? How far, in a rotation, how far apart are they? If I think about the angle rotation. It's a 180. It's a pi rotation, isn't it? That's not an accident. Okay. Let's do the next one. This one says go negative 4. Negative 4 would be here to the left, correct? And then rotate negative 3 pi over 2. Which way do you want to rotate if you're going to go negative from this point? And I have to go up, right? Because I got to go clockwise. So I have to go up. I need to go around 3 pi over 2 from that point in a clockwise manner. So I'm going to end up right here. So my point D will be here. Is this okay? I know the negatives are a little bit weird, right? It takes a little bit of practice. All right. So one thing you might notice, and this is something that we've talked about before, is that you might get multiple representations of the exact same point. For example, if I rotate around, say, pi over 2 or 5 pi over 2, I end up in the same spot, don't I? So certainly, if I rotate this much and this is my theta, well, I would end up at the same place if I do theta plus a multiple, or if I do theta plus 2 pi, don't I? We end up in the same spot, don't we? Or if I do add 4 pi or add 6 pi or subtract 2 pi. Okay? So this point here would have the same coordinate, or sorry, it would end up in the same spot if you added or subtracted any multiple of 2 pi to it. You would end up in the same spot, right? This is different than what we do in rectangular coordinates or in Cartesian coordinates, right? In Cartesian coordinates, there's one and only one representation. In polar, there are multiple representations for the exact same point. We also notice that when we have a negative r value, it's a little bit weird, right? If this is my r, negative r would be down here, right? We agree with that? That's how we got to start to plot the points, isn't it? If this is my theta here, I could do something to this point and make it end up at the exact same place by adding pi. You told me that before. If we add pi, I would end up in, basically those 2 points were pi apart, weren't they? So another way to represent this could be negative r, use the same theta, but add pi to it. Or subtract pi. I mean, I can still play the 2 pi game all day long. So if my original coordinates were r theta, I can do r comma theta plus any multiple of 2 pi. If my original coordinates were r theta, I can do negative r and then add pi to my theta and end up in the same place. So as an example here, one way to represent 1 comma 5 pi over 6, I can use the same r, but add multiples of 2 pi. That's one way to do it. That's an easy way, right? That just gives me all the angles that are coterminal with 5 pi over 6. We did this way back at the beginning of the semester, didn't we? Yeah? Okay. What if I want to change it to a negative? So if I want to change it to a negative, what do I need to do to this point, this angle first? I'm going to change it to a negative. Yeah, add pi or subtract pi. Either way works. So if I add pi, I would get 11 pi over 6. And then again, from there, I could do the add 2 pi game all day long. So again, if it keeps it positive, angles here stays the same and then do coterminal angles. If it's negative, add pi and then do all the coterminal angles from there. We've talked about coterminal angles. It's been a while, but we've talked about coterminal angles before, right? Basically, that's all we're doing here, is just coterminal angles. All right, we'll play more with polar coordinates on Friday. And again, we'll do a quiz on Friday over solving equations. Okay. Have a good one. We will see you on Friday.